So for our colloquium today, we are very pleased to have Sir Michael Atiyah, who I think needs no introduction. As you know, we're lucky to have him here for a couple of months, and he has kindly agreed to give a colloquium for the maths department. Sir Michael's title is Points, Flags, and a variety of other topics that I think you can already see on the blackboard.
Okay, thank you. Well, this is the end of a long day for some of us. And so some of you fall asleep during my lecture, I'll quite understand. And if I do the same, you'll understand. Now, what I'm going to talk about, first of all, it has a connection with the talk I gave here at the Simon Center earlier on, which I'll explain. But it's independent of it, so if you weren't there, it doesn't matter. Secondly, material is quite old. It's not, when you get to my age, it's hard to keep producing new results. So these papers which I'm talking are really quite old, but there's still an excuse for talking about them. First of all, they appeared in rather obscure journals. Do I have a laser pointer? Or? No, maybe that doesn't matter. Anyway, these are the two papers I'm going to be talking about. My first one, joint paper with Roger Bilavsky, and it appeared in the Bulletin of the Brazilian Mathematical Society, not the kind of journal you rush to every morning to read. And the second paper appears in the Chinese Annals of Mathematics. Now, this is about 10 years ago. Now, nowadays, everybody knows that the world economies that are really going to flourish in the future are those with big land mass populations. Russia, Brazil, India, China. You could say I was very far ahead of the game. 10 years ago, I realized that. So, since I'd already published in Russia and in India, I had to publish in Brazil and China. So that's why they're there. Well, there are other reasons as well. And so the first of these two is the one I'm going to be basing myself on much of the time, but the second one has a little subordinate clause to it, which I'll explain. So I'll start by going again over the material I covered in my lecture here. Let me see, is it all visible? There we are. And the question was posed to me about 10 years ago by two physicists, Michael Berry and Jonathan Robbins. And they asked me a very simple question. Is there a continuous map from the configuration of n distinct points, ordered points in R3, which I've written Cn of R3, into the flag manifold, that's the unitary group divided by the maximal torus, or you can think of it as a set of orthonormal vectors, in Cn, which is compatible with the obvious action of the symmetric group on both sides. Now, both these spaces are extremely well known to all geometers. They're simple spaces, much studied, fundamental in lots of areas. When I was asked this question, I immediately thought the two possibilities: either the answer is trivially yes or it's trivially no, and certainly it's well known. And it wasn't. None of those were true. So this is the beginning of my investigation. Now, in my lecture at the Simon Center, I didn't solve that problem, but I gave what was a potential solution. I showed how, given a set of points x1 to xn in R3, you could in a very elementary way construct n polynomials in one complex variable, p1 up to pn, each defined up to a factor, and the conjecture was that those polynomials were always linearly independent. That was a conjecture. It's still open, and there's a bottle of champagne going, and nobody has come back since I gave the lecture to claim the bottle of champagne yet. But they've still got a chance. I'm not leaving till Tuesday. Now, I'm not going to repeat the arguments or give you the construction, but that's what I described there. So, put in more formal language, this would give you a map from the configuration space of n points in R3 into the non-singular matrices, if you like, the coordinates of the polynomials, divided by the complex diagonal matrices, which refers to the non-zero scalars in the polynomials. But of course, the unitary group, complex linear group, retracts onto the unitary group, and so this complexified space can be retracted down onto the ordinary compact flag manifold. They are homotopy equivalent, and the homotopy can even be done compatible with the action of the symmetric group. So from the point of view of a topologist, it doesn't much matter whether you end up in the compact space or in the complex model. But geometrically, it may have an important difference. And one difference may appear when you look at the properties of this map, as I constructed it. It's a natural geometrical construction, and therefore it's compatible with the action of the Euclidean symmetries. The Euclidean symmetries act on both by translations rather trivially, and the SO rotations act in a not so obvious way, but you make them act on the matrices, so the map is compatible with that action. And the same thing I also mentioned, there is a hyperbolic version of the conjecture where you replace Euclidean space by hyperbolic 3 space. And that, the conjecture looks exactly the same. You construct polynomials, you get this map, and now it really is important that you're ending up in the complex space, because the natural symmetry group of hyperbolic space is not the Euclidean symmetries, but is the hyperbolic symmetries, which are the complex group SL2C, and that naturally maps into GLNC by the irreducible representation of dimension n. So the hyperbolic version lives naturally in this complexified group anyway. So that's the topic of my lecture here a few weeks ago. Now I'm going to carry on in a different direction, because although the version with hyperbolic geometry is a nice generalization, there is a totally different generalization going off in a sort of orthogonal direction, which I want to talk about today, and is the subject of my paper with Roger Bilavsky. So from this point of view, the generalization goes another altogether different direction. We first observe that the configuration of n distinct points in R3 can be described in a rather more complicated way as follows. You think of n points in R3, of course they're given by 3n coordinates, and you think of that 3n dimensional space as the tensor product of the Lie algebra of the maximal torus of UN, the diagonal matrices, tensor with R3. Now that space, Lie algebra of the torus, is acted on by the Weil group of UN, which is a symmetric group, and divides it into well-known chambers, and you take 3 copies of that, you tensor with R3. And now the condition that the points are distinct says that xi is different from xj, and that's interpreted more formally by saying that in this space, Lie algebra, the torus tensor R3, you remove a certain subset, delta, which is union of linear subspaces, delta alpha. Each delta alpha is a subspace of codimension 3, which is the kernel of what we call the root homomorphism. The root maps are maps of the Lie algebra into the real numbers, but you tensor with R3, you get maps into R3, and the inverse image of the origin is then codimension 3, and these delta alphas are just those as you vary over the roots. The roots of unitary group are linear forms xi minus xj, so saying that you keep away from those just says that the points are distinct. So I'm just observing that this configuration space of R3 has a Lie theoretical description, and now you can replace the unitary group by any compact Lie group, and you can construct the same kind of space. Namely, you take any compact Lie group, you take its maximal torus, you take the tensor product of the Lie algebra of the torus with R3, you have the root planes, which give you codimension 3, you remove that set. What's left, I'll call the configuration space of the group, and just write as C of G. So you generalize from the original picture in a direction involving Lie groups by observing you can replace the configuration space of n distinct points in R3 by a certain space associated with any compact Lie group. And the role of the symmetric group is now played by the Weil group of the Lie group. And so the natural conjecture, which is now a theorem, is written at the bottom there, and that's the content of my paper with Roger Bilavsky, is that it is in fact a natural map from this configuration space of G into the flag manifold of the group G, G divided by its maximal torus. That's also called a flag manifold. And it should be compatible with the action of the Weil group on both sides, that is a natural action on both sides, and as a bonus, not asked for by Michael Berry, but as a bonus, it's compatible with the action of SU2 on both sides. Now SU2 acts on R3 by just rotations through SO3, and the action of SU2 on the flag manifold is through a particular representation of SU2 in the group, which we'll come to later on. And so this is the theorem which is in that paper of mine with Roger Belaskis, and provides not only a solution of the Berry-Robbins conjecture, but a generalization to all Lie groups, which is very satisfactory. But it doesn't actually answer the original conjecture I raised last time, because that map is given in a totally different way. This map, as you'll see, is not very explicit. It comes by solving, or implicitly, by solving some differential equations. You can't write it down. And it lands up naturally in the compact flag manifold. The other potential map was written down explicitly, elementally, but it landed up in the complexification. Well, they might really be the same map in disguise if you push one into the other one, and that's one of the questions that are still unsolved. So I want to explain a bit more about what goes into this theorem and consequences of it. So first of all, and this goes back to the beginning, when I was first asked, is there a map between these spaces? And you try to say, no, it can't possibly be. I'll give you a counterexample, or I'll show some contradiction. The first thing you try is, if there is such a map compatible with the action of the various groups, then you look at the effect on cohomology, and you look at what happens on both sides, and you might get a contradiction. The cohomology rings don't match up. But in fact, they do. And so if you have a map, now I told you there is a map, and I'll do this in the case of a general Lie group now, there is an induced homomorphism in cohomology. You might just take rational coefficients, which maps the cohomology of the flag manifold into the cohomology of this configuration space, and it's compatible with the action of the vowel group. Now, the first thing to notice is that there are very different dimensions on the two sides. The flag manifold has a dimension for un, n times n minus 1. And for the configuration space, its dimension is 3n. So one grows linearly with n and one grows quadratically. And so the cohomology on the left-hand side there is big, and a lot of it has to get killed off when it goes to this much smaller space. So you might say, well, it's not a very interesting map in cohomology. Most of it goes to 0, which is a bit disappointing. If it's a nice map, somehow you feel that it should, capture the cohomology. But it does capture it to some extent already, obviously. The important thing to point out is this, that these configuration spaces I've been talking about, they're got by removing linear subspaces of codimension 3. If I replace R3 by R2, for example, then I'd be replacing taking codimension 2. And that would be if you complexify the Lie algebra. And those spaces have been much studied a long time. In that case, you get the complement has a fundamental group generated by little loops around these things. And those fundamental groups, for example, for the unitary group, that gives you what's called the braid group, whereas the vowel group is the symmetry group. You get by permuting components. When you just take R and you complexify, you get C, you get a fundamental group. The space is not connected, but it's not simply connected. When you replace R2 by R3, you get a space that's simply connected because you're cutting out codimension 3, and what surrounds the point is a two-sphere, not a circle. So you've killed the fundamental group, but now you've got a lot of two-spheres. Now the two-spheres are the things that you see in the flag manifold. The flag manifold has a lot of interesting two-spheres, which in fact generate its homology in some sense. So this map is a much better map than the one which is much older and more familiar, which is based on the complexification, because that really doesn't interact. On the one hand, you have a fundamental group, on the other side you have cohomology coming from things at dimension 2, and they don't live in the same world. Here, we capture the stuff in dimension 2. Now, that's the one good point. Secondly, although the map is not an isomorphism by any means, you can observe something interesting if you compute the Poincaré polynomials of both sides. That's to say, the polynomial whose coefficient of t to the nth is the nth Betti number. The Poincaré polynomials of both these spaces are easy to compute, because in fact these spaces are really iterated vibrations of things by induction on n. And so the Poincaré polynomial of g over t, for example, for the unitary group, is written down there, is 1 plus t squared times 1 plus t squared plus t to the fourth. These are the Poincaré polynomials of objective planes of different dimensions up there. And the Poincaré polynomial of the configuration space is a very similar thing, but it goes up differently, 1 plus t squared, 1 plus 2t squared, 1 plus 3t squared, and so on. And notice that if you put t equal to 1, nice thing happens, both of these become factorial n. And factorial n is the order of the symmetric group. Now that's not an accident, obviously. So there is obviously something interesting just in that observation there. And we want to somehow pursue that a bit further. Now notice also that the symmetry group acts on the cohomology of both sides. I mean, this Poincare polynomials is a way, when you put t equal to 1, just measure all the Bethe numbers together, because there's no odd cohomology at all. There's no cancellation. So the total cohomology has rank factorial n. And each side is acted on by the symmetry group, and it's no surprise to find out that that action is the regular representation. In both sides, the symmetry group acts on the cohomology, on the total cohomology, via the regular representation. But it grades the thing according to the dimensions. And although the representations say on both sides, the dimensional grading is different, because they don't match up the spaces of different dimension. So something interesting is going on here, and how can it be about that you have the same representation, but the gradings are different? What's happening? And also the same remark applies to all the Lie groups. In every case, you get the regular representation of the Weil group on these spaces. Not hard to see why, by the way, because they have free action. So the explanation, what can we do with that? Well, after a lot of thought, I realized there's a very simple way to make sense of that, and that's the following. I'm told if I put this in the right place, you'll see both the top and the bottom, just about. Well, you'll see the top, and later on you'll see the bottom. The first is, I haven't yet used the compatibility of these maps with the rotation group, or SU2. I told you that wasn't asked for by Berry, but in our construction, that's the case, because it's a geometrical construction. And so that being the case, you can talk not about cohomology only, but about equivariant cohomology. Now, equivariant cohomology is defined whenever you have a group acting on the manifold. You can mix the manifold and group together, and the simple way to do that is you form the fibration over the classifying space of the group, whose fiber is the manifold, which is given by the group action. This gives you a space that I've called the group here S, which is just SO3, and so you'll have the classifying space BS, and over it you'll have a space MS, which is fiber M, and then all cohomologies in question now are modules over the cohomology of a point. The cohomology of a point, you see formally, is the cohomology of the classifying space. Over the rational numbers, the cohomology of the classifying space of SO3 is a polynomial ring in one variable of degree 4, which represents the first Pontryagin class. So all the modules above are modules over a polynomial ring in one variable of degree 4. And now, since our map between the flag manifold and the configuration space was compatible with this action of this group, we can look at the induced action in equivariant cohomology. And now we have this theorem, which is the content of the second paper, which just says that what you might hope happens, that now the induced map in cohomology is practically an isomorphism. What do I mean by practically an isomorphism? Well, formally, both sides are modules over a polynomial ring. The map is injective, and it's almost surjective. The co-kernel is a torsion module, and it's annihilated, in fact, by a power of U. Torsion module supported at the origin in geometrical terms. So, in very concrete terms, what does that mean? That means that if you take a basis of the ordinary cohomology of both sides, and there are natural bases, then this induced map is given by a certain matrix of polynomials. The matrix, the size of the matrix, is the order of the Weil group, so factorial n in the case of UN, and it's a matrix of polynomials, so you can expand it as A0 plus A1 times U plus A2 times U squared, and so on. And if you think of this, what this does to the cohomology, what it does is that A0 is the original map, which is no equivariance at all. But when you A1 times U, U has the effect of decreasing degrees by 4, because U is dimension 4, and that counts in the whole geometry. And so these higher terms are successively reducing degrees by 4 at a time. And that's the way that the much bigger cohomology can be squeezed into the small cohomology because of the additional effect of this variable. Now, let me just show you how that works. Very simple, very concrete. Here is the first example of interest, is to take U3. In the case of U3, the Poincare polynomial of the flag manifold is 1 plus 2t squared plus 2t to the fourth plus t to the sixth, and you're happy to note that's nice and symmetrical as Poincare duality implies. The Poincare polynomial of the configuration space is 1 plus 3t squared plus 2t to the fourth, and it stops there because its dimension is low. When you map the top one to the bottom one, what happens? Well, you see we have to get an isomorphism, essentially. What happens to the t to the sixth term goes down to one of the t squared terms and takes that 2 into a 3, or if you like, this one kills that one. And so you've reduced the dimension. A1 is the term that reduces the degree by 4 and matches them up. And the general story is just similar. You expand this one out as a very big power series, and these other polynomials, A1, A2, and so on, just push them back down again in just such a way that they match up and they are compatible with the symmetric group, and it all fits very beautifully together. It's a very, very nice, simple exercise. So that this map we constructed really does capture the cohomology on both sides, if you include the symmetry of the story, which is natural. So that's really showing that this map gets to the really, it takes this small configuration space and puts it into the heart of the flag matter. It actually captured all the cohomology in some sense, which is very satisfying, and that is definitely not the case when you stick to the more classical picture of using the complexification. That doesn't touch the cohomology, but this one does. So this is actually very, I think, a nice aspect of the story. That's why I mentioned it besides the proof. Now let me go back and say something about the method of proof of the theorem which I proved with Roger Bilavsky. Now this proof relies on a very beautiful differential equation called Nahm's equation, which has since become very famous and is used all over the place. It's probably the simplest equation to appear in the mathematical physics literature, and it has a long history and it's all sorts of things. But as an equation, it's extremely simple. It's an equation for 3 elements, T1, T2, T3, of any Lie algebra, depending on one variable t, real variable, and it satisfies a system of differential equations which just says that the derivative with respect to t of t1 is the bracket of t2 and t3, and similarly with the cyclic permutation. So it's a system of first order differential equations defined for any Lie algebra. Those are Nahm's equations. In the case of a compact Lie group, you can formulate it a slightly different way. If you take the Lie algebra of the compact Lie group, for example, the Lie algebra of the unity group, and then in that case this differential equation can be viewed as the gradient flow of a function. There is a function on the space. The space is made up of the direct sum of 3 copies of the Lie algebra, and so on that space you have a function, and that function is just naturally the one invariant function of 3 things on Lie algebra of a compact group. You can think of it as T1 inner product, because you've got a compact group as inner product of the bracket of T2 and T3, but it has appropriate symmetry. It is actually alternating form, and it's the one invariant alternating form in degree 3 on the Lie algebra of a compact group, which corresponds to the unique harmonic 3 form, which in turn corresponds to the 4-dimensional cohomology class of quantity-Argand class. So it's the basic invariant function you can associate to a Lie group, and just the flow of that function is the Nahm equation. It's a very sort of fundamental thing for the theory of compact Lie groups, although it was only discovered by Nahm in recent times. The particular case of SU2, this goes back a long way, is the equation for a spinning top, and is well known to be a nice equation that you can solve. This is what's called an integral system. There's a very beautiful theory of solutions, and is very extensively studied. So this Nahm equation is the key to understanding this theorem. Now, Nahm's equations turn out in a variety of places, but what's important about the equation is you have to put in the right kind of boundary conditions. So there are 2 types of boundary conditions. You're on the line, you've got one variable. So one end, let's say 0, is the end point. You're going to put a condition, and now the kind of condition you can put down there is that the solution is not regular at that point, but has a pole. But the pole has to be a simple pole. I resist telling the story about Mark Katz. I can't resist the story. Mark Katz was a famous Polish mathematician, some of you may know. And I remember a man with quite a sense of humor. And I remember him telling me this story. He said, yeah, this student he was trying to teach him complex variable theory and trying to explain to him what singularity the origin was of the function 1 over z. And he tried, the student couldn't get the answer, and finally said to him, look at me, what am I? Ah, a simple pole. Well, I can't read. Now, if you write down a function with a simple pole, it starts off with the residue term, ai over t, plus higher terms. If you write down Nahm's equation and you look at the coefficient of 1 over t squared, you see that the facts that they have to cancel just lead you to the equation that says a1 is equal to the Lie bracket of a2 and a3. These are just the basic equations that define the Lie algebra of SU2. So what the residues do is give you a homomorphism of SU2 into the Lie algebra of the group. And it's well known there are a finite number of conjugacy classes of such homomorphisms for any Lie group. For the unitary group, they lead to the, well, in some other version, they lead to the classical Jordan forms, and they can be described explicitly. I'll say a bit more about them later. So you fix, basically, which one you want to look at, and that will give you the boundary condition at the origin. At infinity, you can do something different. You could now assume that these matrices, depending on t, become constants at infinity. They go to a constant limit. If they go to a constant limit, then the derivative term drops out, and all it says is that t2 bracket t3 is 0, so the three matrices, three elements commute. So you get a commuting triple of elements of the Lie algebra. And in general, they will lie in a unique maximal torus, in the Lie algebra of a unique maximal torus, and they will be a conjugacy class. There will correspond an orbit of the Weyl group acting on that set of triples. So that a triple will be a point in sort of three copies of the Lie algebra, and the action of the Weyl group is just the one we talked about before. So you see this configuration space will appear as the asymptotic values of this solution of the equation. Now, there's a general principle, which I use the word principle. You know, when politicians use the word principle, be careful. They mean that there aren't any. But when a mathematician uses the word principle, he means it's not actually a theorem, but it could be a theorem under certain circumstances. It's a principle. And here, this principle it really lives very much at home here in Stony Brook because it was invented here. And in physicists, it goes under the name of supersymmetry. And the famous paper of Martin Rotchek and Nigel Hitchin, which was worked out, I think, in Stony Brook about 20 years ago, which explains this in mathematical terms, what supersymmetry means to physicists. And as a consequence of that, you get a lot of beautiful theorems, and I just call them a principle here. And what the principle says is that when you set up Nahm's equations and other equations of similar type, then the solution spaces with given boundary conditions, they're not unique. They in general will depend on certain moduli space. That moduli space is a manifold whose dimension is a multiple of 4, and that has a natural metric on it, which is a hyperkähler metric. Now, hyperkähler metric is a metric where you have the tangent space is really a copy of the quaternions. That's why it has to be multiple of 4. And on each tangent space, you have an I, a j, and a k, which act like the unique quaternions, and these are covariant constant under parallel transport by the metric. If you just focus on, and they all have square minus 1, each of them gives rise to a complex structure, in fact a Kähler structure, and there's lots of them because you can replace I and j by k, but you can equally well replace them by any linear combination whose square is 1. So you have a whole 2 spheres worth of complex structures. And these are a beautiful class of manifolds which really only came to the fore as a result of work with physicists for good reasons. That is that examples are rather thin on the ground. If you are like a traditional mathematician interested in compact manifolds, for a compact manifold to be hyperkähler, if for example dimension 4, it either has to be flat like a torus or the very unique, exceptional, famous K3 surface, and that's potentially it. But physicists tend to quite often like non-compact manifolds, things that go to infinity. And there are lots and lots of them, and the ones that turn up here are typically of that type, and so they're actually rather useful. And now this situation of Nahm's equations having moduli spaces which are hyperkähler manifolds was exploited by Peter Kronheimer. and he got some beautiful, very beautiful papers. And I'm going to, what Roger Belowski and I did was really to use his ideas in a very simple form. But so the word for our purposes, what we did was to use the following. We specified we're going to use Nahm's equation on the on the line. You could also take it on intervals, where at one end you specify a homomorphism of the SU2 into the group or into the Lie algebra if you prefer, and you fix that homomorphism. You actually fix it, not just the conjugate, you actually choose it. And then at infinity, as you go off the other direction, the matrices will commute. You get a commuting triple, and you assume they're regular. That's they don't they keep away from these Weil chambers, and you also look at it up to conjugacy. You only fix the conjugacy class, and you put all that together, you end up with a beautiful picture. First of all, you'll get hyperkähler manifolds in general, and these hyperkähler manifolds will be parameterized by the points in this configuration space, as I called it, of the group. So each point in this configuration space, which is one of these commuting triples of infinity, which has been specified in the boundary condition, really, over it there is a manifold of dimension multiple of 4 with a natural hyperkähler metric. And you get a family of these hyperkähler metrics. And in fact, they all can come from one bigger manifold on which a torus acts by what's called the hyperkähler moment map, and these are the hyperkähler quotients. So it all fits into a very beautiful theory. But the important thing is that there are the solutions form a manifold of dimension 4k, and there is a map. From the Morris construction, if you just look at what happens in infinity, you get a map from this manifold into the flag manifold. And it's compatible with everything in sight. It's compatible both with the action of the Weil group, which acts as usual on both sides, and it's also compatible with the action of SU2. Now you know what we mean by the action of SU2 on the other side, because we've specified rho to be the homomorphism in the first place. So that tells us how it's supposed to act. So there's a theorem. That's a general story and we have choices depending which rho you take. And I told you there are finitely many. Now, let me list for you the interesting cases. There are 3 special cases of particular interest. The first is what's called when rho is regular. The word regular is unfortunately heavily used in mathematics, but in the case of UN, this means it corresponds to the irreducible representation of dimension n. But every Lie group, there is a unique conjugacy class of regular representations. I'll say more about that in a moment. In that case, from the point of view of trying to construct interesting examples of hyperkähler manifolds, it's very dull. That's why Kronheimer didn't bother with this case. That's the case with the manifold of dimension 0. It's a point. And so in that case, the map we had before, which mapped this collection of manifolds over the configuration space, just maps the configuration space itself into the flag manifold. And that's the map of the theorem that I've quoted. You get the map of the theorem of Belowski by choosing a point in the configuration space. That determines the conjugacy class at infinity. Then there's a unique solution of Nahm's equations. We specify with rho being regular, and that gives you, then you look and see where you ended up in the flag manifold at the end, and that's the map. So it's actually a very simple case. Now the other 2 examples are the ones that actually Kronheimer was interested in, and more interesting. If rho is what's called the subregular homomorphism SU2, that's also a Euclidean distinguished class. It's a rather interesting one. In that case, the manifold has dimension 4. In that case, the manifold you get, well, at least when the groups are of type ADE, are the famous ALE spaces. They're asymptotically locally Euclidean. They're nice, well, in this dimension 4, they are Kähler-Einstein manifolds, much studied, very important, a lot of applications, and they all come out systematically this way. When rho is 0, you think an extremely dull case, that means there is no pole at the origin. So you look at solutions of Nahm's equation to regular, all the way from 0 to infinity, then you get the moduli space is in fact just the complexification of the flag manifold. And the map you get then from that into the compact flag manifold has to be just some kind of unitary retraction. But you get it as part of the theorem. Now both examples 2 and 3 were the ones studied by Kronheimer. We just used the case 1, which is rather dull, because it's what we wanted for the proof of the theorem. Now, I've got a comment at the bottom there which tell you a bit more about these homomorphisms SU2 into a group. The homomorphisms SU2 into a compact group under complexification correspond to homomorphisms SL2C into the complex group. Now, SL2C has a unique, in its Lie algebra, has a unique nilpotent class, this off-diagonal term. And that then maps into a nilpotent element in the Lie algebra of the complexified group, and the nilpotent elements in the complex Lie group form actually an algebraic variety, and that algebraic variety has a finite number of strata, which are preserved by the action of the Borel subgroup, I guess it is, and there's the general point, those correspond to the regular ones. Then the ones just below that are a codimension 2, the first stratum, those are the subregular ones, and so on. You go all the way down, there's a whole sequence of until you get to the bottom one, which is the identity 0. So the structure of this nilpotent variety, the structure is the classification of nilpotent orbits in the complex Lie algebra, or the same thing as the conjugacy classes of homomorphism SU2 into the compact group. That's how you get them. And they're very extensively studied. Now, let me wind up with a few open questions, because one of the reasons I wanted to talk about this again is that there are some things open questions which arise, and that's part of the reason why I wrote the original paper. Well, first of all, what is the relationship between that conjectured polynomial map I talked about in my last lecture, given by elementary methods, to what you get by solving Nahm's equation? Now, Nahm's equation is an equation, you prove a theorem, the existence of a unique solution, but it's a differential equation, you don't lay your hands on the solution. It's not that simple. So it's not really explicit. But nevertheless, they give you, at least from the point of view of homotopy theory, equivalent answers. And so in some sense, one must be related to the other. Exactly how, I don't know. And of course, part of that hides the fact that the first one only conjectured. If you knew how to relate them, you'd have solved the conjecture. So the conjecture and the bottle of champagne are linked in some sense, the second bottle of champagne, if you like, if you can not only show that the map is, the polynomials are independent, but show how these two are actually related. And the natural guess would be that they are related by the natural contraction mapping. The second question related to this is the following. I told you that in the special cases of Nahm's equation, the third case here was the case when the moduli space of solutions of Nahm's equation are actually the complexification of the maximal torus. And actually the way that Kronheimer formulates that is nicer. If you look at a compact Lie group and look at its adjoint representation, then it's well known in general, or you think of it as the coadjoint representation, the same thing. The orbits have a natural symplectic structure, discovered by Kirillov in general. And it's known in the case of compact groups that those orbits are actually Kähler manifolds, and you get a variety of Kähler structures as you vary within the orbits. And what Kronheimer proved is the corresponding thing happens if you take the complex Lie group and take its coadjoint representation. So its orbits are now complex automatically, but they're also formally symplectic. And if they're complex and symplectic, and if you solve the right differential equation, you'll get a hyperkähler structure, and that's what he's done indirectly. So he's got constructed hyperkähler metrics on the complex coadjoint orbits, which are the generalizations of the things which are well known in the compact case, and it all comes out of Nahm's equation. It's a very beautiful story, these are the generic orbits, where it actually is the complexification of the full flag manifold. The degenerate orbits correspond to smaller manifolds. Then there are also of course, the nilpotent orbits. By the same methods in general, all of these things have been shown to have nice hyperkähler metrics. So the second question, part of my open question, is really, what is the relationship, if any, of that third case, where this complexified the outer appears in connection with the Nahm's equation, to the fact that it appears in this other conjectured formula here? No, I've thought a bit about it, but not very deeply. Somehow there are two worlds. There's the world of complex things and there's the world of unitary things. And here we seem to be uncertain which we're in. And lastly, and also related to the first two questions, is there an analogue of this polynomial map for a general Lie group? For the unitary group, we wrote down some polynomials, conjectured they're independent, and they would give you this map. We know that for any Lie group, there is a map into the flag manifolds, but is there somehow natural corresponding complex map into the corresponding complexified torus? It seems plausible that there should be, and it would be nice to find it. But elementary methods of construction aren't so simple. I mean, the flag manifold of the general linear group is just n independent vectors modulo something. For the other ones, you have a lot of orthogonal group. You have to look at certain constraints, and it'd be hard to do it as explicitly. But theoretically, you might expect to be able to, that it should exist with somehow a similar relationship with the compact groups if we knew what it was. So there's a whole host of questions here which are all equally unsolved. Now there's a different set of questions which is much deeper, and this is so I will be much skimpier about this, but I can't resist saying it because this is partly why I was originally interested in this question. And this is a relationship to some very deep work of Kazhdan and Lustig. And in a very brief summary, what they did was to look at the following sort of questions. With every Lie group, you have what you can associate what's called a Hecke algebra. And the Hecke algebra, from one point of view, is a deformation of the Weil group algebra, but it deforms it involving a parameter q. So it's called a q deformation, or a quantum deformation. And what you get at the end of it is a module over the Fourier-Laurent series in Q and Q inverse, which is also the representation ring of the circle, which is also, if you like, the equivariant, I think this should be S3 there, equivariant K3 of the two-sphere. But either way, the Hecke algebra is, you can write it down in terms of, you write down the equations for the Weil group, for example, for the symmetric group, and then you modify one of the equations by adding a parameter q in it, and becomes Hecke algebra. And these have a wide history and background in number theory and so on. And what Kazhdan and Lustig do is to construct the irreducible representations of the Hecke algebra systematically and for all groups using equivariant K-theory of certain spaces. Now, the thing which intrigued me was that the spaces they use are exactly the same as the spaces that turned up in what I've talked about so far. There are these manifolds, which are hyperkähler manifolds, these coadjoint orbits, except that in Lustig and Kazhdan work, they work purely in the context of algebraic geometry. So for them, they have algebraic varieties, they have complex numbers, but my point of view here was involving also things which had metrics. So the hyperkähler metrics are a much strengthened version of the complex story. They really go from the complex numbers to the quaternions, and somehow there should be much more information in there. As I pointed out, going from the complex numbers to R3, which is the imaginary quaternions, is what leads you to these two spheres of the flag manifold. You don't see those in the algebraic geometric picture. So I like this version, and the fact that all the spaces which we came across appears in the work of Kazhdan and Lustig in exactly the right places began to suggest some speculation. Now, I think I should distinguish between three levels. Conjectures, which are precise and experimentally checked a few times, and you got a strong chance of believing that it's proof. Then there is speculation. Speculation is a bit less precise. You think there should be some connection between this and that, but you're not quite sure what it is, and you speculate. And finally, there is something called observation, where you're afraid to make any speculation, you just point out some things. So I shall do a bit of speculation and a bit of observation. So first of all, my first remark is that when I looked at these maps constructed before, I looked at the induced map in cohomology and also in equivariant cohomology. But equally well, you could look at the induced map in equivariant K-theory. In fact, the formulas usually are better. Everything I've said so far about equivariant cohomology works in equivariant K-theory. And in K-theory, you tend to be able to work over the integers, not just over the rationals. So there is a corresponding story in equivariant K-theory, and it's equivariant K-theory that Kajal and Lustig use in their story. Now the idea I had, and this is a speculative idea, was that, you see, Kajal and Lustig construct modules over the Hecke algebra. They're representations. So the picture I have is of the configuration space of these groups, in some sense, is the Hecke algebra in disguise. That's a speculation. And that the modules, the bundles over it, are the modules. I mean, geometrically, that's what, logically, if you have a ring and the module sits above it. And so my hope was that I could understand all their stuff just by looking at this picture. With some details, if you go into the details, it matches up very nicely. And using equivariant K-theory systematically through the whole story. Well, now, when I first wrote the draft of my paper with Roger Bilowski, I put speculation center stage. Now, this is why I would like to prove. Here is some evidence, and we sent it into a journal that has high standards, and they just wrote back and said, well, we're sorry, we don't publish speculation. You know, you've got a theorem, we'll be happy to print it, but we don't publish speculation. So they rejected the paper. One of the few papers in my life that's been rejected. So, you know, what do you do when your paper is rejected? We took it back, we rewrote it. So the theorem I mentioned before, appears front line. You know, we prove the following theorem. Then the speculation appears down the bottom, rather sotto voce. And then we send it to the journal in Brazil, where I had friends, and it was published. So, the reason why I published in Brazil is precisely that some other journal turned it down. But of course, you see, the journal might have turned down Poincaré because he didn't prove his conjecture, or Fermat because he didn't prove it. I mean, if you turn down everything with no proofs, you lose all the excitement. So posterity will show whether the editor was right or not. Anyway, we haven't proved it yet, but it's very tempting, and I keep coming back to it. And one of the reasons I offered to give this talk is I think here's another chance to have another think about it, and perhaps before the lecture comes about, I'll have a proof. Well, I got closer, I had new ideas, but time was short. There were too many people to talk to here, so I didn't quite make it. But now let me give you an observation. Why should I have thought of the speculation? Well, I gave some very vague ideas, but something more precise. And here is this precise observation, which you can take quite independently of everything else. Let me start with something which is very well known in topology. Suppose you have a fibration, a map Y, manifold or space Y mapped over a space X with fiber F. Then it's well known that the fundamental group of the base acts on the cohomology of the fiber by what's called monodromy. You take a cohomology class, you drag it around, you see what you get. Very well understood process. If you want a more formal definition or fancier way of saying it, do it the following way. Lift everything to the universal covering of X, call it X tilde. On the universal covering, your point P down below has a lot of transforms under the action of the fundamental group. Let Q be one of them. Then the action of fundamental group moves the fiber over P to the fiber over Q. So obviously it gives you an isomorphism for the cohomology of the fiber at P to the cohomology of the fiber at Q. Now, join P and Q by a path. The space is simply connected, so there's a unique homotopy class of paths, and the path is an interval. The interval is homotopically contractible, so you can contract the two, and therefore there is a canonical isomorphism between the cohomology at P and the cohomology at Q. You put together that canonical isomorphism with the map induced by pi, and you get an action. Now that's a very long, complicated way of saying what I said before in one line. But there's a reason, because this is the thing I want to focus on now. And that reason, the question is the following. What happens, and this is a very simple, naive question, you can, independent of anything else, what happens in an equivariant situation? Suppose now we have exactly the same as before. We have a map Y to X with a fiber, and we have a fundamental group. But in addition to that, we have another group, let's call it S, which typically might be a circle, which acts on everything in sight. Acts on the whole space, acts on the fibers, moves them around, acts on the base, and it moves compatible lifting to the total space. The question is now, you might say, suppose you've got a fixed point of the circle action in the base. Then the circle has to act on the fiber over it. So the fiber over it has an action of a circle, so it's an equivariant cohomology for that circle action. So you might think, now I'm going to get an action of the fundamental group on that equivariant cohomology. You'll get more information because I got another group. But look at it more carefully. Well, now let's do it carefully. We lift everything to the universal covering. We go up to x tilde. Have the same picture as before. Fundamental group acts. It moves you from point P to point Q. It gives you a nice map, which is assuming that the lift and the circle can be figured together, that you'll get an equivariant map. Therefore, an isomorphism of the equivariant cohomology over at P and at Q. Now, how do we want to join them together? Join a path. It's simply unique because it's up to homotopy, because it's simply universal covering, but it's not invariant under the circle action. And why should it be? The fixed points are fixed, but outside it'll move things around. You can't do much except rotate that path. When you rotate the path with the two fixed points, you get a two-sphere with the north and south poles. So instead of getting the interval, you find you've got a two-sphere with a circle action on it, which plays the role of the unit interval. And if that were contractible, you could go ahead. But it isn't, unfortunately. That is not contractible, and there's something interesting there. So what is it that you've got left with? Well, I leave it to you like that. What you've got is this sphere, and the sphere, and I suppose you're looking at cohomology. You can look at the equivariant cohomology of the two-sphere for the circle action. That's an interesting module. Equivariant K-theory, equally interesting module. That's not a trivial object. So somehow you'd like to get an action of the monodromy on this equivariant cohomology, but the obstruction is that these two spheres are lurking around to get in the way. But we know precisely what they are. So the question really is, what can you do? What kind of algebraic structure can you extract from that picture which generalizes monodromy? I told you exactly what you got. You've got a lot of modules sitting at points. They're not there are group actions, move them around, but between any two, there is this two-sphere, and these are, here you work out what the equivariant cohomology is, and you know what it is. Well, that's a lot of data. How do you turn that into something more conventional, like the monodromy? Well, my idea was, what you would do were to replace the symmetric group, which might have been the fundamental group, by the Heck algebra, and that is, the Heck algebra is doing what you'd wanted to do, somehow incorporating that action. That's the idea. So you see, there's some sort of madness in my philosophy. If you replace equivariant cohomology with equivariant K-theory, you get much closer now to the Lustig-Kazhdan story, because the equivariant K-theory of this is the finite Laurent polynomials. And notice that what is the equivariant K-theory of a two-sphere with respect to the circle action? It's well known what it is. It's a free module on two generators. In fact, the whole thing is a ring. So you can describe it as a polynomial ring in one variable over the ground ring with one relation, quadratic equation, t minus q times t minus q inverse. Or you put q to the half if you want. That is the equivariant K-theory of the two-sphere for the circle action on it. What is Heck algebra? Well, the Heck algebra of two elements. If you just had the symmetric group, it would be a group algebra of two elements. Just have sigma squared equals what, plus or minus 1. And the Heck algebra is the quotient of the polynomial ring in one variable by the single quadratic relationship t minus q, t plus q to the minus 1. So a very small difference in sign. Okay? What's the difference in sign between friends? So, it looks terribly, terribly tantalizing. Of course, you've got to realize that the equivariant K-theory is not the answer, because those are commutative rings, and these only for 2 points is the Heck algebra commutative. In general, Heck algebra is a deformation of the group algebra of the symmetric group. Symmetric group on more than two letters is, of course, not commutative. So the Heck algebra is not commutative, so it's not a commutative ring. But somehow, one feels that in that picture we have of points joined by paths and two spheres, if you look at it the right way, perhaps you can extract from it this kind of model. I've tried and tried again. I feel I'm almost there, and then the next morning I wake up and it just doesn't quite click, but you feel it just around the corner. So, I hope somebody here will have more inspiration than me, so be able to see how to do it. And the same is true for all the groups. The story says universe is a sort of universal story for all the Lie groups, or Heck algebras for each one, the Weil group, and all the pictures are exactly the same. So the whole Kazhdan-Lustig theory seems to be beautifully geared for this story. And yet, we couldn't do it, and so the paper was rejected, you know, and that's why he went to Brazil. But I hope here the Simon Centre is more open to speculation and conjectures than observations. That last remark was an observation, by the way. I was telling you about, I was raising the question, what do you do about monodromy in the presence of additional symmetry? How do you put that together? And it's a problem. I mean, you can see exactly what the problem is, but how do you try to describe the output? I've thought of modern ideas about categories and quivers, and maybe there's some fancy terminology that people have discovered which tells me that's what this thing is. But in my more naive language, I don't know exactly what it is, and I'd like to relate it in particular to the Hecke algebra, but I could be wrong. Anyway, I've given you enough additional problems to work on. If you didn't solve that first problem with the bottle of champagne, you've got another chance to work on some of the other problems. Okay.
Questions? Well, I have a question about when you construct this hypercale manifold.
Yes.
The regular case where the dimension is 0 and that's the point.
Yeah.
The subregular case where the dimension is 4.
Right.
What if I try to continue? So
Well, you get all the other ones too. And the other ones are all manifolds of multiples of 4, and you get these things like the complex coadjoint orbits of all types, and they all turn up in this characteristic story. They're all, in terms of groups and centralizers, they're well known as algebraic varieties of the complex numbers. They're well known. What they don't see is the hypercalometrics, because that comes out of the Nahm's equation of use.
I think of the classification of compact hypercale manifolds.
Yes.
Where it's complete, but there are examples.
These aren't compact. These are, of course, they're not compact. They're all
If I try to compactify any of this, is there any chance?
compactify.
Is there any chance that the complexification of anything like that would ever be compact?
No. These are always non-compact. But I think it's the one thing I learned when talking with physicists, that the obsession with compact manifolds for mathematicians is a mistake. I mean, okay, compact manifolds are nice, but so is Euclidean space. You know, and you've got to get away. After all, in the old days, people compactify things in order to bring infinity under control, made it projective space, and they've loved it, and it's very useful to do that. But you shouldn't always insist on things being compact. You should allow infinity in. Infinity is a good thing, and for physicists, it's pretty well important.
Any questions? Well, thanks, Sir Michael, again.